What is up, YouTube? Today we're going to talk about binary search trees. Binary search trees. You may have noticed that I have just circled this root part of this tree. And that is the first thing we're going to talk about. In every binary search tree, or also known as BSTs, there's going to be a part that is called the root. And in this case of our binary search tree that I just squared with a red um marker, this 25 is going to be our root. Our root is basically going to be the first part that we write down, right? In a binary search tree, the first rule and the second rule as well is everything relative to our root that is going to be on the left side of our root is going to be smaller. Everything on the right side on the root is going to be bigger. Now, that just might not make sense for now, but let's just look at our BST real quickly. So our root is obviously 25. Let's just look at 20. Is 20 bigger than 25? It's obviously smaller than 25. Is 22 smaller than 25? Yes. 10, 5, and 12 are all smaller than 25. So everything on the left side is going to be smaller than our root. However, everything on the right side is going to be bigger than our root, right? So let's look at 36. 36 obviously bigger than 25. 30 obviously bigger than 25. 40 bigger than 25, and so on, so on. So everything on the right side is obviously going to be bigger, right side obviously, and left side obviously going to be smaller. And this is how binary search trees work. The reason we use binary search trees in the first place is it's really easy to search for values. For instance, let's just say we want to search for values 38. In an array where you have all these values, let's just say, how many values is this? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Around 12. I may have missed one or two or overcounted, but let's just say we have a size of 12. If we want to look if this array contains a certain value, we have to look at the whole thing basically. But for binary search trees, so this may take up to 12 comparisons, but in a BST binary search tree, all we need to do is search for our wanted val. And in the process, we can delete half. Let's just look at 38. Is 38 bigger than 25? Obviously, yes. Then we're going to delete the whole half of this part right here. We're going to look at 36. Is 38 bigger than 36? Yes, obviously. So we again can delete half of it out. We're going to look at 40. Is 40 bigger than 38? Obviously less. Yes, we're going to go to the left side now. Now, boom. So all we needed to do was 3 to 4 comparisons compared to an array. So our binary search tree is way more faster than our original array. And an array, it costs about O of n, while in a binary search tree, it takes about log n. Because obviously we're going to cut half of it each time. And this is how a BST works. So let me just delete all of what we just did real quickly. And now let's go to adding and deleting vals in a binary search tree. So when adding and deleting a val, it's actually really simple. But obviously adding a value in is way more easier than deleting a val. Let's just say add. We want to add value x. X can be any integer possible. Let's just say we want to add value 50. Is 50 bigger than 25? Yes, it is. Is 50 bigger than 36? Yes, it is. Bigger than 40? Yes, it is. Bigger than 48? Yes, it is. All we need to do, put 50 on the right side of 48. Let's just do a random example again. Let's just say we want to add values 17 this time. Let's just use our green. We're going to compare 17 to 25. Is 17 smaller than 25? Yes. Is 17 smaller than 20? Yes. Is 17 bigger than 10? Yes. Is 17 bigger than 12? Yes. Then we're going to put it here. So for inserting values, all we need to do is go to the correct position and insert them. However, now we go to our deletion, which is kind of more hard and intricate, but complex, but it's still very simple concept. So for deleting, we have three scenarios. When we have 0 children, we have 1 child, and 2 child. These are our three scenarios. Let's look at these, right? Let's just say we have values 5 in here, right? Let's just say we want to delete 5. And 5 is obviously our first case where it doesn't have children. When I mean children, 10 here has 2 children. 5 doesn't have values beneath it, so it has no children. 30 has 1 children because it has 28 under here. So that's what I mean by child. Okay, so let's look at 5 here. 5 doesn't have any children, so all we really need to do is cross that value out. And that's it. 17, no children. Just cross it out. 15, no children. Cross it out. And that's all we really need to do. So for 0 child, all we need to do is cross it out. Boom. We have covered deleting 0 children. Now we look at values that have 1 child. Values such as 12 here. Let me use a different color. Let me use purple. 12 here. If we want to delete this, we can't just delete this, because if we delete 12, we're going to lose 17 as well, right? Delete 12, we're going to lose 17 as well. So what we need to do, essentially, right, is we need to connect 10 to 17. And then a lot of you may ask, what happens to the 12? If we connect 10 to the 17 and disconnect 12, then 12 will automatically be erased in the computer. Same goes for values such as 30. We're going to now connect 36 to 28 instead of 36 to 30. So this is how you delete nodes that have 1 child. Lastly, we're going to talk about values that have 2 children. So that goes for 36. Let's talk about 36, for example. So 36 has 2 children, 30 and 40, right? If we want to delete 36, the first thing you need to do, always when deleting 2 children, is you have 2 steps. You have to go to your right node. If you want to delete 36, we need to go to the right node, which is going to be 40. I'm going to triangle this. And the next thing you need to go do is find the smallest value, which is in this case 38. And that's it. After you locate 38, you put 38 here. And you delete 36 and delete 38 as well, right? That's all you need to do. So we're gonna swap places. First go to the right and then go to the smallest part. Then we're gonna swap places with the current node that has 2 children, right? And that's it. Okay, guys. If you have any questions, please leave a comment. Thank you.